Hi y'all, Raya here, and today we're going to be learning about rates of change in natural and social sciences. In other words, real-life applications of derivatives. But before we begin, some prerequisites. Hopefully, by now, you know a bit about how to find derivatives, such as using techniques like the chain rule and laws for exponents. If not, click on these two wonderful pigs and you'll be sent directly to some videos regarding that. Okay, you ready? Let's start. Question number 1. A particle moves in such a way that it is s of t equals 3t cubed minus 6t squared plus 3t meters to the right at time t seconds. How quickly is it traveling after 2 seconds? Okay, so let's say the position graph looks something like this. This is a question about speed, and velocity at essence is just change of position over time. So you can see how the change of speed over the change of time. In this case, the position is actually s, because math reasons. And so this slope is just delta s over delta t, which you can see it should be pretty evident that the velocity is just thus the derivative of the position function. This is key. In calculus, if there's a problem about asking about change, it's going to be about derivatives. So let's take the derivative of this function. Using the power rule, we can get v of t equals 9t squared minus 12t plus 3. So we can just, with this function just gotten, we can just plug in 2 to get 36 minus 24 plus 3 equals 15 meters per second. That's our answer. So what else can we do about our little newfound adorable little velocity function here? Well, we can find the zeros of it. We factor it out, and you'll be able to see that this function is 0 when t equals 1/3 and 1. So what does that mean? Well, this is the velocity function. So at moments 1/3 seconds after it begins and 1 second after it begins, it's not going to be moving at all. It's stationary at these 2 moments in times. Additionally, it gives us a little insight about the position graph. But that's enough digressing. On to the second problem. Question number 2. Given such conditions, when is it speeding up and when is it slowing down? Well, alright. So we already have the position function here, and our velocity function we got just now. So first let's get our acceleration function. So that's just taking the power rule of this, 18t minus 12, and speeding up and slowing down. So as it turns out, a particle is speeding up when the velocity and the acceleration have the same sign, and it is slowing down when velocity and acceleration have opposite signs. Let's take a simple example, like a bouncy ball. Its trajectory should look something like this. Initially, the speed is very large, but as time goes on, it slows down as a result of the opposite direction, acceleration. Acceleration is always going down in this case, and the ball here is velocity up. So it's slowing down as it goes up. However, when it reaches the peak of its motion, it starts falling down, and as it falls, it goes faster and faster, because the velocity is negative bound, and acceleration is going down. See how when velocity and acceleration are against each other, they're going to slow down, but when they're in the same direction, they're going to speed up. Boom. So, back to the question. We know from before the velocity is 0 at 1/3 n1. So we can write that in a little table like this. 1/3 1. By plugging in numbers in these intervals, we can show that the velocity is positive from 0 to 1/3, negative from 1/3 to 1, and positive from 1 onwards. Similarly, we can see acceleration has a different 0 at t equals 2/3. So we graph that out as well. Since it's continuous, we can do something like this. These are polynomials, so it's just going to be positive, negative, and in this case, negative, positive, because this slope is positive. So you can kind of see where that's coming from. So with this knowledge and the idea of these differing signs, we can show where this is speeding up and where this is slowing down. Here and here, you can see these are both negative and both positive going onwards. So we will say that the particle is speeding up on the interval 1/3, 2/3, union 1 to infinity, and it is slowing down on the interval of 0 to 1/3, union 2/3 to 1. So that is our answer for that. Be wary on stuff like tests. You should explain why this is speeding up because of the signs. But yeah, that's our answer to question number 2. All right, final question. Question number 3. The company of Ayor's atrocious apples can produce X apples at the cost of C of X equals 5 ln 0.5 of X plus 0.02 of X. What is the marginal cost of producing the 10th apple? Again, this problem is one regarding the derivatives, although it may not seem like it. The marginal, or difference function, is the derivative of the cost function. You can just memorize this like an old textbook, but I think it's far more interesting to see why this is. Let's say we have a graph that looks something like this. This would be our price, and this would be the amount of apples we produce. As you can see, the marginal price, or the price between 2 points, is just delta dollars. These are apples. Delta dollars over delta apples, or the change in apples, or the change of price over the change of apples. So once again, we can use derivatives to estimate the marginal price at a point. So we can go through this pretty quickly then. The marginal price at X is just take the derivative of this. This is a chain rule, followed by the derivative of ln x plus 0.02, which is just power rule. This simplifies out to become 5 over x plus 1 over 50, and we want the 10th apple, so we'll just do it at x equals 10, yielding 1/2 plus 1/50th, which simplifies to 1/13, 25ths, or just 0.52 cents. Which, come to think of it, seems kind of expensive for an apple. But then again, what were you expecting from a company called Ayor's Atrocious Apples? Huh? Well, that just about wraps up this video. If you want extra practice, the worksheet and answers can be found in the links below. And hey, I might just do other stuff for this channel in the future. So if you're looking forward to more math shenanigans in the future made by yours truly, subscribe, like, leave a comment, blah blah blah, you know the drill. Alright, this is Roy Yan saying goodbye.